All right, let's look at this question. I haven't looked at it in detail other than to spot there's an inclined plane. Let me read it now, and let me read the question first to figure out, is it complex enough for me to use the standard strategy, or should I do something else? So two boxes of mass M, same mass, but they are labeled differently, A and B. They are at rest. A is on level ground, all right. So I have A on level ground, and while box B rests on an inclined plane tilted. Oh, okay. And then it's asking for expression for normal force. Yeah. So the easy part of the question, you might do things like M times G, and just get the answer quickly that way. Standard strategy is really for questions that are not that easy. If you only had easy questions to deal with, then you wouldn't need a standard strategy. And that is what standard strategy is for. So let me spell out the standard strategy. The standard strategy says to approach a force analysis question, you start by drawing free body diagram, and you define coordinate axis. Usually you do it in the direction so that the x-axis is along the direction of acceleration. For this question, we'll probably end up doing it that way, although I can give a different rationale in a bit. Step number 3 is break forces into components or decompose force into x and y components for two-dimensional problems. Step number 4, and this is what steps 1 through 3 were building up to, you write down net force equation. Net force is equal to mass times acceleration, Newton's second law. And step numbers 1 through 3 are designed to help you do this as a streamlined, kind of organized way as possible so that you don't forget forces. So I feel like I understood everything there is to know about A, so let me not do anything with A. Let me draw a free body diagram of B. So I have free body diagram of B, and I feel like they are saying at rest. And let me read into that one thing. They are at rest and they are staying at rest. So for block B, I have gravitational force pulling it down. That must not be all the forces that are on B, because then it should be accelerating downward, and it's not, it's at rest. So you think through it and you remember, there's probably normal force from this surface of contact. And then you ask yourself the question, did I draw all the forces? And you should have the answer, no. With these two forces, there's no way you can get zero acceleration. You'll have acceleration that looks like this. So there must be another force. And you have my types of force lecture, and the main point of the lecture is basically every force other than gravity, you need to be able to identify what's touching what in order to identify that force. Here, with this block B, it's really simple. There's only one thing that's touching box B, just this surface here. You identify the one force, normal force, and this is where, even though the question didn't mention friction force, if you are trying to hold on to my reading of at rest, you need to infer that there must be a static friction force. Otherwise, you can't get zero acceleration that the situation would imply. So this is the kind of situation where you need friction, so you introduce friction. So now I can convince myself I've drawn all the forces. This can be made consistent with the zero acceleration. Having drawn all the forces, my complete free body diagram, now I define my coordinate axis. With the zero acceleration, I do gain a fair deal of freedom because my acceleration has no direction. I could just define my axis this way. Nothing stops me from doing that. But I would say you should use that freedom to kind of simplify your setup. Here I have two forces that are in the direction of along the incline, perpendicular to incline, so I should just make that my x and y direction. I think that's gonna simplify the rest of the problem solving. So I'm just gonna do it that way, not overcomplicate the problem for myself. So having defined the coordinate axis, now I can decompose the only force that needs to be decomposed. The only force that's not along the x or y direction, gravity. So this is the x component, this is the y component. I think we are given the angle theta, and go through the geometry. That angle should be this angle here. It's not this angle here. It's not that. I think this does come down to just geometry practice. Draw auxiliary figures, figure out what other angles are what, and I think that will help you figure out. It's this 90 degrees, yeah. So that can help you figure out this is 90 minus theta, and then that's theta. So then this side must be mg sine theta because it's opposite to the angle, and this side must be mg cosine theta because it's adjacent to the angle. Good. Step number 3 is done. Step number 4, write down Newton's second law equations. I got two-dimensional problem, so I need to write it down for net force in the x direction and net force in the y direction. Net force in the x direction, I have the friction force, Fs, minus the x component of gravity, minus mg sine theta, is equal to 0. And y component, I have normal force, minus the y component of gravity, mg cosine theta, is also equal to 0 because total acceleration is 0. So that's my standard strategy. And standard strategy, it doesn't solve the problem for you. It's not meant to solve the problem for you. Otherwise, it couldn't possibly be standard because it would depend on what the question asks. It's meant to land you at a place where you can basically answer any question that the actual question asks. So the actual question asks, what is the normal force on box B? And you look at it and you realize, oh, I can use this equation. The normal force that's here is box B, and everything here is known except for the normal force. So solving for the normal force on box B, that should be mg cosine theta. Yeah, so when a question asks normal force, you need the y component equations. That's why I don't forget writing it down. Let me just click through here. mg, and then there's a trig function, cosine theta. And I think not closing the parentheses will be fine. Yeah, they just automatically close it because without it, it makes no sense. Good. All right, I got correct expressions. Compare the two forces. Here I have these answers, so this divided by that should just give me cosine of theta, I think. Don't know if it's meant to be more complicated than that. Oh yeah, and consider the ratio of the masses. I think it meant to say ratio of the normal forces. Yeah, let me report to author. There might be actually a typo in the in OpenStax itself. I'll go check after this. So given the ratio of the normal forces being 0.1, okay, here's where I do need a calculator. So it's saying basically cosine of the angle is 0.1. So I need to do arc cosine of 0.1, and I want that in degrees. Now, if you don't want to, press enter, then you could do kind of on-the-spot conversion here by multiplying by 180 degree divided by pi. 84 point, is that right? That feels wrong. Yeah, I guess that is right. Otherwise, it's for small angle, the cosine of the angle would have been close to 1. I mean, I'll put it in. It kind of doesn't make a lot of physical sense, but yeah, it is correct answer. And I guess I think it would have been nicer if this was like 0.9. If it were 0.9, then we would have gotten more reasonable looking angle. But yeah, that's the answer. Yeah, and that's this question. Thank you.